Hello, linear algebra student. This video is for chapter 2.1 part 2. So let's continue with matrix multiplication. And in this particular video, we want to talk about the properties of matrix multiplication. We know how to multiply in the first video, which is most popular is row column rule, and you need to know that the the restriction is the number of columns in the first matrix has to equal to the number of rows in the second matrix. So let's continue with how if we can multiply A and D. A is 2 by 2, D has 2 columns, D has 3 rows, so it's not possible, right? Because when you do row and column, the 3 is too much, okay? What about DA? So D has 3 columns and A has 2 row only, so also not okay. What about BD? B is 2 row and two columns. D has 3 rows, so also not possible. What about DB? D has 3 columns and B has 3 rows, so this would work. So we can just look at compare the first columns and the second row to see if they can multiply. Another thing that we want to talk about is properties of matrix multiplication. So for numbers, we know if it's there's all these rules: associative, distributive, scalar multiplication, right? So for number, if we have 3 times 4 times 2, we can do 3 times 4 first and then times 2, and it's the same as 3 times 4 times 2 first, right? That's called associative property. That means you can do them in any order you want. For matrix, it's the same. You can do associated properties, but you can see that there is no commutative. Okay, so for numbers, 3 times 4 is the same as 4 times 3. That's called commutative. But in matrix, that does not work. So they are not the same. So it is associative. If you multiply it in orders, that's okay, but not commutative. So just make sure that AB is not the same as BA. And sometimes you can multiply AB, but you can't even multiply BA. And even if you can multiply both, they would not be the same. But for the distributive rule, they are okay. So if you want to add B and C first before you multiply with A, you can do A multiply B first and then A multiply C and add them. You can also do the right distribute law, but you have to keep the position. So if you do B plus C first and then multiply A, you would have to do B times A first plus C times A. And then if you are to do a scalar times A and B for products, you can multiply to A first or multiply to B first. And this is also important. If you multiply identity matrix to a column, to a matrix that is equal to the matrix. So that's why it's called identity. So we can illustrate that. If I have a 2 by 2, and then my A is, let's say 1, 2, 3, 4, or any number. So if I multiply them, I do row column 1 times 1 plus 0 times 3. So the 0 times 3 doesn't work, or it's just 0. So I end up with 1, right? Row column, so 1 times 2 plus 0 times 4, so again 2. Row column, 1 times 0, that's nothing, plus 1 times 3, so the 3 would show up. And then lastly, 0, 1 times 2, 4, so 0 times 2 is nothing, 1 times 4 is 4. So you can see that this, after you multiplied it, would just be the same as whatever that you have. I times anything is equal to that matrix. And just remember, it's not commutative. AB does not equal to BA. Also, if AB equal to AC, you cannot cancel A and say B equal to C. The book had a question that showed you that. So if you're interested, look at the book's exercise. And also, if AB is equal to zeros in numbers, we can say either A equal to 0 or B equal to 0, but you don't. here, you can have AB equal to 0, but you can't conclude that A equal to 0 or B equal to 0. It's kind of easy to show if you have 0 alternately, so when they multiply together, they cancel. You can have everything equal to 0, but the individual ones are not. So, for example, we are doing this is to show that non-commutative. Okay, this is to show one example of non-commutative. This is a very important properties of matrices. You have to know that the position is important. So if I do A times B, it would be row times column. So the first is 2 times 3 plus 3 times -1 times plus -3. Then the second will be 2 times 2 plus 3 times 4. And then this one will be 1 times 3 minus 5 times -1 column, right? The last one is 1 times 2 minus 4 times 5. So that would equal to 6 minus 3 is 3. 4 plus, what was it? This is a 4, right? 12 plus 4, 6. 12 plus 4, 16. And then this is 3 plus 5 is 8. And this is 2 minus 20, -18. Let's do B times A. So 3, 2, -1, 4 times 2, 3, 1, -5. Multiply them. 3 times 1 is 6. 6 plus 2 is 8. Okay. Row, column. 3, 3 is 9. 9 minus 10 is -1. Row times column. -2 plus 4 is 2. Row, column. -3 minus 20, -23. So you can see that the numbers are not even the same. So AB is not equal to BA. Now, there are some cases where AB is equal to BA. We'll talk about those in chapter 2.2. But for most part, AB does not equal to BA. So this is a very interesting question. They say if you multiply these two together, for some reason AB is equal to BA, find K so that it works. So we just have to multiply them, right? So A times B, let's see what happened. A times B would be 1 times 1, 4 times 6, 2. 1 times 6 plus 4 times 2, so 6 plus 8 is 14. And then I would do the first row, the second column. So be -4 plus 4K. And then the second row, first column would be -12 plus 6, so it's -6. And then this would be -2, 3 times -4K, so it would be 8 plus 3K. So that's AB. And what about BA? BA, I'm going to write it out actually, because this one is AB. 2K in the front, and then 1, 4, -2, 3. So when I multiply, I do the row here and the columns here. So 6 times 1 plus -4 times -2, so that means 14. First row, first column, so that would be 4 times is 24. 24 minus 12 is 12. This times this will be 2 minus 2K, right? And then the last one will be 2 times 4 is 8 plus 3K. So 8 plus 3K is the same in both. This doesn't help us, but this 2, either this equal to this, and this equal to this. So we can solve either -4 plus 4K equal to 12, or they have to match, right? 2 minus 2K is equal to -6. So let's solve the last one. So -2K would equal to -8K is equal to 4. Is it the same here? So if I have -4 plus 16, yes, that's also K equal to 4. So in both of them, K equal to 4 will make AB equal to BA. Okay. Example 3, if A is a 4×3 matrix, and then you end up having a product of 4×2 matrix. What is the possible dimension of B? So we can write A row times column. B has to be row times column. So this has to match, right? And the answer is this one, R and C. The answer is this. This is the answer, right? How do I say? This is M. This is P, right? So it's M times P. And this has to be N, right? So we have 4 times 3. And then this is 4 times 2. So that means B would be times 2. And then what about the row? Row is the same as the column, so it's 3 times 2. And then the next one is about power of matrix. So if I do, and also transpose. So I'm going to do video 3 on power of matrix and transpose of matrix in the next video.